If you went to scientists and engineers and hydrogeologists who are calculating the 100-year, 500-year event, um, this person was saying that they're probably using a one parameter distribution. Um, they're opposed to Monte Carlo simulation. It wouldn't surprise me if someone with little knowledge of stats made a model based on the normal distribution and came up with something that indicated 500 years. And they probably used an algebra-based intro to stats book model, and they probably resented ever having taken a stats class, and that people in geology will tell statisticians that everything you learned in your academic career is wrong, that statistics is all theoretical nonsense. And I was utterly horrified by this. I worked for the US Geological Survey in water science, hydrology, and there are amazing people in the USGS in hydrology, in amazing people in terms of their statistical abilities. A lot of hydrologists come out of civil engineering programs, and there are civil engineering programs across the country that are very, very strong in statistics. And some universities come to mind. I won't list them all because I will invariably leave out some important ones. But there's some really phenomenal hydrologic statisticians. Certainly, there's some civil engineering programs that don't offer any statistics at all, and that is a problem. But there are people passionate, knowledgeable, phenomenally good at math that work in hydrology. So this was just like, you are stabbing all of us. This is horrible. So I responded. Here's my response. And some of this I'll be talking about throughout the presentation, so I won't go into all of this. But basically, it was that people have been working on flood frequency, precipitation frequency, storm frequency models since at least the 1960s. There have been a number of government's guidance documents. There have been really great committees that have been working on this issue, revising standards. It's not a one parameter normal distribution that's used in the United States. It's a 3-parameter distribution. Other things are used in other countries. It is an imperfect model, and there are ways the statistical community could help improve it. And here's a bunch of resources. So I posted this, and I was surprised at the number of people that emailed me afterwards from the American Statistical Association discussion board, that they really appreciated me adding this, and that they too thought this was not good, not professional, and they appreciated having these resources. So I want to talk to you more about flood frequency analysis and where the community could use more help. So some definitions and terminology: flood frequency, something that might be called the 100-year flood, is also called the 1% annual exceedance probability. And it would be a flood that is so large that on average, the law of large numbers, over a long period of time, it would only happen once every 100 years. The public has a hard time often with the concept of a 100-year flood, because you could have back-to-back 100-year floods. And in fact, Ellicott City, Maryland, 2018 had 2 significant flash floods in 2 years that were considered 1,000-year floods. And that was just flabbergasting to people. Another case where some people were saying statisticians, hydrologists are stupid, because how can you have 2 1,000-year floods back to back? We know from assuming that they're random events that can happen. Some time ago in the USGS, we were told we shouldn't use the term 100-year flood because it's confusing to people. The alternative was annual exceedance probabilities, and I don't know that that's really more helpful for the general public. So, certainly communication is an area where the community could use some help. There are federal nationwide guidelines for calculating the 1% AEP, the 0.5% AEP, the 100-year flood, the 500-year flood, the 1,000-year event, whatever you want to call it. And we need nationally consistent standards for nationwide flood damage abatement, managing water resources. If you're building a bridge, you need to calculate these flood flow frequencies. That bridge may, the different ends might be in different states. So we need national guidelines to have consistent, uniform results. Other countries have other guidelines. Some have more well-defined standards than others. They're not the same internationally, though. And so there's been quite a evolution in federal guidelines, and currently the guidelines are in what people in the flood frequency community call Bulletin 17C. So people that do flood frequency analysis talk about Bulletin 17C all the time. Like that is the standard for flood frequency analysis. And really smart people have been working on this for a long time. We know that there are some shortcomings, and there's certainly opportunity for future work. But to address some of those criticisms that came up in the American Statistical Association dialogue that they probably use a normal distribution and they were unhappy even having to use a normal distribution and go beyond algebra. Distribution choice is a big topic in flood frequency analysis. Bulletin 17C, as I mentioned, uses a 3-parameter distribution, log Pearson Type III. So it's assuming the data follows a Pearson Type III distribution, the logarithms of the data. So it's defined by a mean, variance, and skew. Some countries use a generalized extreme value distribution, and that is also used for rainfall. You can use a skewed normal distribution. There's generalized Pareto, generalized logistic, Weibull, asymmetric exponential power kappa, Wakeby. And a colleague of mine, William Asquith, compared flood frequency results for very rare low frequency floods using a number of these distributions. You can go beyond 3 parameters, but certainly that's more complicated, more subject to overfitting. Is it worth it? So then another big topic in flood frequency analysis is the fitting method. We have data, annual observations, the annual peak value at stream gauges that measure the volume of water all across the country. It measures the volume of water passing by that point. And the USGS has an extensive database. All of our stream gauges, we record the annual peak value. And sometimes an important caveat is that that is not actually a flood, particularly when you get into semi-arid, arid areas. The river may not have gone out of its banks in a dry year, but we still record that highest value to get a sense of the long-term variability, probability of floods. So we have data, we make a distributional choice, and we need to fit the data. And there are lots of options for fitting the data. And a colleague, a USGS colleague, Tim Cohn, developed this expected moments algorithm. And it can include non-standard flood information, historical and paleo floods that can be expressed as interval estimates or threshold values. We know this historical or paleo flood peak was less than something. So that is what we're using in Bulletin 17C, because the ability to put in interval estimates and more uncertain estimates. It's really useful for extending our period of record and understanding the system better. But you can also use product moments, maximum likelihood, L moments, percentiles, maximum product of spacings. And again, this report I had mentioned before, done by William Asquith, does some comparisons of these fitting methods. And under certain circumstances, one of these might be better than the others. The major advantage of this expected moments algorithm is that you can put in these interval estimates. So when you do flood frequency analysis, there's software to do this. The US Geological Survey has software. The US Army Corps of Engineers has software. People can write their own code to do it. You get numerical results and a visualization like this. And this is for a particular stream gauge on the Moose River at Victory, Vermont. And so on the bottom, the x-axis, we have annual exceedance probability in percent, so 1%. And this is the annual peak discharge in cubic feet per second. So a volume of water passing by that point. And this comes from our stream gauges all across the country. So if we look at the 1% annual exceedance probability, otherwise known as the 100-year flood, we go up to this red line. So it's about 5,000 cubic feet per second. So if I was building a bridge in the vicinity of this, or putting in a large culvert, doing some other infrastructure projects, I would have a sense of, if I want this to last for a long time, I should build it to withstand a flood at least this big. And this is used for all kinds of infrastructure. Sometimes people are putting in small culverts, and the design life for that culvert might be 25 years. So I don't build it to the largest flood. I build it to a reasonable flood and know that at some point I'm going to have to replace this. But if I'm the Nuclear Regulatory Commission, where I'm concerned about long-term storage of nuclear waste and extraordinarily rare floods, I did a study for the Nuclear Regulatory Commission where we went to 10 to the -6 probability or the million-year flood. And there's some problems with that concept, because if that flood is so rare, it only occurs once every million years, is the river even there over a million years? It may change dramatically, but yet there's a probability, a tiny probability, that that million-year flood happens next year. So they have to have some form of estimate. And then this calculates error bounds, and we can see the blue lines. The error bounds get wider in the tails, which is not a surprise to statisticians. But this is as floods go, a pretty good looking flood frequency curve. There are problems that arise at many sites though. And those of us dealing with environmental data know that outliers can be a problem in the tails. And one of the issues is low outliers. As I mentioned before, some years it's not actually a flood, particularly semi-arid, arid areas. You can get zeros, you can get very low values, and that affects the fitting of the distribution. And really, these low values we don't care about. We can handle those. Maybe some of these cause a little bit of erosion. We can deal with that. We've got culverts, bridges generally that can deal with all of these low values. We want the curve to fit better at the higher end, where we are more concerned about accuracy. So Tim Cohn and others worked on this multiple Grubbs-Beck test to identify low outliers, and that's incorporated into the flood frequency analysis methods in Bulletin 17C, along with the expected moments algorithm. And these are identified as low outliers, and then they're treated as interval estimates. And so essentially we're discounting the influence of these values so we can get a better fit on the higher end. So one of the problematic boxes checked. We know there can be problems with outliers on the high end. And this can particularly happen with large, very rare events. And there's an event, this is Rapid Creek in the Black Hills of South Dakota, where in 1972, there was a huge, huge flood that blew out of the water any previous floods we had ever seen there. And even since then is way above floods we've seen. I think 300 some people died So it was a massive, serious flood. And we can see this, we can't even see the whole curve here. The program's having a hard time even plotting it because it skews things so much. We have these super wide error bars at the end going up towards 10 billion cubic feet per second, which is not physically possible, and all this uncertainty. So with the expected moments algorithm and people that do paleo flood studies, we can get estimates for some past paleo floods. We can get estimates from some historical floods in the past. And all these gray lines, it's kind of a technical thing that I'm not going to get into too much, but we have this regular annual data. And then when we get into historical and paleo floods, we have gaps in the data, and you can make some assumptions about those gaps in the time series, in that if it had been above a certain value, it would have showed up in the paleo record or in a historical newspaper. So all these lines represent some of those years with missing data, and we know that it was less than some threshold values, and there's some subjectivity, but oftentimes you can be pretty confident in that. So this is that 1972 flood. Paleo work showed that there are bigger floods out there. Bigger floods have occurred, and then found some smaller floods as well, and some historical counts that are point estimates. We can incorporate that information into flood frequency analysis, and now we get a much better fit. Still not perfect, but for environmental data, really this doesn't look too bad. The error bounds are much narrower. We're now like at 11 million as opposed to 10 billion. You know, there are questions as to whether or not this is physically possible, but we can see that it dialed that down a lot. And we have some really rare floods in here. So there are ways to help deal with high outliers. Another issue that people have dealt with to show that they are not just using algebra and even troubled by using algebra is the skew parameter. So 3-parameter distribution, mean, variance, skew. The skew is sensitive to the particular sample of floods you have, and the skew you use can really affect this high end. And so people have come up with methods to get a regional skew that you can use to weight that skew at a particular site. So we have multiple stream gauges in a region. We can look at the skew at all of these sites, which have varying periods of record, and some of the watersheds are bigger and some are smaller, and get a regional skew and use it to weight or tune that skew at the site. And that can really help some of that upper end, huge error bars, incredibly large estimates. Sometimes it often improves the fit, not always. But here's an example of this Rapid Creek one. This is at site skew. And if we use a regional skew estimate based on more sites, more data, we see, I guess before this was a weighted skew option that I showed you. So if I had just used the at site skew, we had gone from 10 billion CFS without the historical peaks. Getting these historical peaks in and a better sense of the high end distribution got us to 1 billion. And if I use the weighted skew, these floods still fit in here well, but the upper tail seems more realistic. Still huge error bars given that we have a log scale here, but reduced the uncertainty. Still a lot of uncertainty, but that's to be expected with these really rare flood events. So people have been working through these issues, improving the method, but there are still some issues, and you might be thinking of some of them already. The assumptions behind the data, it treats this stream gauge record as a random representative sample of outcomes from the flood population of interest. So we're assuming IID, independent, identically distributed, homogeneous data. So there are a number of challenges to this. I don't think I'll go into all of them, but climate change. So if we have 100 years of record, the precipitation regime might be quite different. And then of course, land use change. The system may have urbanized. There might be a lot more impervious surface that delivers water more quickly to the stream. So this assumption is problematic, and it kind of depends on where you are in the country. This assumption seems to work well in some places where the system is pretty stable. Other places that are subject to long-term climatic persistence and sudden change, this was probably never a good assumption. So some time ago, it was suggested in the literature that this stationary assumption, consistent mean variance skew, is dead. And this has been a hugely cited paper in hydrology because of their great title, Stationarity is Dead, Wither Water Management. So, okay, that assumption is dead, what do we do? And that has generated a lot of work too. And some great journal article titles, which is not something we often get to have fun with, but Stationarity, Wanted, Dead or Alive, Getting from Here to Where, Flood Frequency Analysis and Climate. Stationarity is undead. Uncertainty dominates the distribution of extremes. So there's an argument that, yeah, but every model, there's a problem with it. And there's so much uncertainty, so much variability in floods. Maybe we have some bigger issues than some small, relatively small non-stationarity in the data. Negligent killing of scientific concepts, the stationarity case, saying that the stationary assumption is very useful and allows us to do these things. And if you don't give us an alternative, killing it is negligent. So Bulletin 17C mentions some of these issues, the concerns about climate change, climate variability, long-term change, that this should be considered in flood frequency analysis. And I was part of a study that looked into some of these things. What changes are happening? How are floods changing? What is causing the changes? How could we adjust frequencies for that? Bulletin 17C brings up some of these questions, but it does not tell us how to do them. It's future research needs. And so there's been a lot of papers coming out on this, techniques for assessing non-stationary extreme events, but also it's a challenge, untenable non-stationarity. If you go into the non-stationarity realm, and say Bulletin 17C is untenable, what do you do? So there's been a lot of work that's come out even since then. Study that was started by colleagues of mine, I eventually became a project lead for it. But we looked at sites across the country, and the colored areas represent the basins covered by the stream gauges we looked at. And we developed a multiple working hypothesis framework for what might be changing floods. And these are the things we considered: precipitation changes, multi-decadal climate variability, snowpack changes, air temperature, withdrawals, agricultural land use changes, urbanization effects, and then even really some rare things. Glaciation, volcanic activity, earthquakes can change systems such that the flood regime changes. And that's really rare. And generally you would be pretty confident of that if there was a change caused by that. Some of these other things, it's more difficult to say. So we looked at these multiple lines of evidence and documented what was going on from what multiple lines of evidence at these sites. And then, what do we do that information? How do we incorporate that into flood frequency analysis? So some colleagues, as part of this project, did some Monte Carlo analysis, looking at different ways to adjust peak flow for trends. in peak flow, which is one small aspect of that. So of this, sometimes there is a trend up or down in peak stream flow. An area is getting drier, so it's trending down. An area has gotten wetter, so it's trending up. Increasing urbanization, more impervious surface, so maybe you're seeing larger floods. Not all things causing changes have that clear of a signal, so adjusting for a trend is one possibility of looking at this. And then, do we use a different distribution? And if you use a highly parameterized model, is it worthwhile? And how well do these models fit observed peaks? And then you have to look at tail behavior. So there are a lot of issues with this. And if someone's really interested in that, there's a paper, you could email me, I could get you that. There are a lot of other papers on methods for potential non-stationary flood frequency analysis. Some existing practices include you do standard bulletin 17C analysis, and then you add some kind of safety factor or percent onto that. This is what I think the 100-year flood is. I know things are changing, so I'm going to build something to a larger value for protection. And then the question is, what is the safety factor? And then that kind of depends on other state, local, federal regulations, insurance, kind of goes beyond the scope of what we do in the USGS. Updating other products to be more representative. A lot of people, when they're building infrastructure, also look at something called Atlas 14 precipitation estimates. Some of these across the country, particularly in the Pacific Northwest, have been very out of date for a long time. These have a stationary assumption built into them too. There's been some criticisms of this product. This is another area in terms of flooding storms that scientists are struggling with. You can simulate hydrologic response under historic, current, future land uses and do some simulated flood frequency analysis. You can look at trends in annual flow and update your data set based on those trends. But Bulletin 17C does not provide specific guidance on this topic. If we have a trend in the mean, is there a climate covariate that explains that? I have several colleagues, one Tom Over might be on today, that have looked at impervious cover and urbanization. That's an important aspect of changing floods, but generally that's one direction and upward. So variable climate provides some additional changes. And we could update to current conditions, but then what is the future? Does that trend continue? Does it level off? Is it a quasi-periodic climate signal that then the trend goes down? We don't know. So then there are a lot of assumptions you have to make about what is the future. And you can come up with some more complicated adjustments. So what do we do? There are lots of suggestions. Nationally, internationally, there is no winning solution yet. And this is an area, other statisticians could help us with. There's a lot of work done on mixed populations because we have this annual flood series and it's treated IID, identically distributed, but in many cases, some of them are snow melt driven floods. Some of them are summer convective system driven floods. Some of them might be spring precipitation mesoscale events with an occasional hurricane thrown in there. As the probability of hurricanes increases in certain areas, that may be increasing the probability of some very large floods. Is there a mixture population you can use? Maybe there's something we can do with bootstrapping to, if you have a relatively short stream gauge record, can you make more out of that? Can we incorporate climate projections into flood frequency analysis? Can we incorporate additional covariates? Colleague Tom Over is looking at panel regression and urbanization, land use information in there. models with variable parameterization, a changing mean, a changing variance. There's so much uncertainty when you get into the second, third, or more parameters already. How much more uncertainty are you inserting into this? And then, of course, visualization and communication tools will be an important area as we move forward on this. And then one thing for all of us to keep in mind is that USGS does flood frequency studies all across the country and provides these numbers to people, but also people in state agencies, consultants, do a lot of flood frequency analysis, particularly when they are, something's going in at a particular site. We may have done a flood frequency study 5 years ago. They wanted to look just at this site in depth. And across state, federal agencies, consultants, there's varying degrees of technical skill in statistics. And so some of the methods that have been proposed out there are so complicated that realistically, they are not going to be adopted, or will only be adopted in rare, very rare cases, like for the Nuclear Regulatory Commission. So how do we bring in more information on changing conditions without making an overly complicated model? And I and colleagues have a project right now covering 9 states in from Montana to Michigan, looking at that question. We're going to test a number of different methods, maybe tweak some methods for non-stationary flood frequency analysis, and do some comparisons and try to come up with some guidance if urbanization is what's going on and you want to go beyond bulletin 17C, maybe this is what you do. And if it's an increase in precipitation, here's a model where you could put some precipitation data in and try to provide a path forward for some people. Again, it will be a challenge for federal state agencies because we need nationally consistent guidance for interstate commerce. And so it likely will be a long time before Bulletin 17D or Bulletin 18 comes out. So things will be in flux for a while, but we hope to help move things in the right direction to adjust for changing climate and land use conditions and get better estimates, because when it comes down to it, even though we know things are changing, people need a number, a target or range for building that bridge, installing culverts, small bridges, building other infrastructure. So it's interesting work that many are passionate about, and many super skilled statistical hydrologists, statistical engineers with great statistical skills are working on this, and I'm happy to be part of that community. So thank you for asking me to talk today, and I'd be happy to take questions if anybody has questions. Or, if you want to follow up on some of these resources, you could email me and I could email you some of these papers.
Thank you, Dr. Karen, for this great talk. And I would like everybody to unmute their microphones and give her a round of applause. So thank you for doing this. And we will take any questions anybody has. Maybe I can start. So Karen, can you please, so how do you see machine learning scenarios fitting into, because it's all, today's age is all about machine learning, and there's a big cross between statistics and machine learning, which is called statistical machine learning. So how do you see that fit into hydrology and flood analysis?
So a couple things come to mind for flood analysis. One is that regional skew. Oftentimes for flood analysis, people are still very interested in a specific site and maybe don't need machine learning to tell them something about a whole bunch of other sites. But when that skew parameter becomes important, fit the higher end and we want to weight it with a regional skew, there's scientists that have spent years working on regional skew and all the intricacies and what sites do you include and do we assign a regional skew based on large basins like the upper Missouri River Basin? Do we give it a regional skew or do we have regional skews for smaller areas? I think machine learning would have a ton of possibility in these regional skew studies where people are incorporating sites all over the nation and trying to find some patterns in skew and assigning regional skew values to certain areas. I think that would be great. And then, as you were asking the question, I thought of, yes. So another thing that people do in hydrology, an important type of study is, as I mentioned, we have these stream gauges all across the country. We use data from these stream gauges, but oftentimes people are putting in a bridge, a culvert, at a site that's not particularly close to a stream gauge. So people have developed methods, regional regression equations, to come up with estimated stream flow statistics, could be low flow, could be high flow statistics, peak stream flow, at ungauged sites. And these equations can incorporate land use information, climate information, and those generally have been large, onerous studies. And I think there would be a lot of opportunity for machine learning to estimate those regional regression equations. And then we can do some truth checking against the actual gauged sites. But I think there would be a lot of opportunity there.
All right. Thank you. I have another question. So I was just wondering how, because at least in my country, in India, usually dams, when you build dams, um, there are a lot of small villages built around rivers, and when you build dam, that creates huge issue about, okay, what if the dam fails? There's a flood. So how is that taken into account with regards to flood frequency, and like how does that impact flood frequency at all when you construct dams and you like in infrastructures of such huge scale that perhaps change the way water flows?
Yes. So one of that's a good question. There's many directions I could go in answering that question. Many things come to mind. One is standard flood frequency analysis, bulletin 17C, has that assumption of independent, identically distributed observations. And we know there's some flaws to that. But when we look at sites that are regulated, where there are dams, that is even more problematic because we may have natural rainflow, inflow from tributaries, but the dam operators have an operating curve, a rule curve they're usually called, to operate that dam for various purposes. So in the spring, they're filling the dam with runoff to prevent downstream flooding, but then in the fall, they're letting more out than you would see naturally in that stream to draw down the dam and have storage for the flood next year. So it is not a natural flow, and there's a lot more serial correlation in it. So in the USGS software, there's a way you can indicate it's a regulated flow, and you can do flood frequency analysis, but certainly there are lots of caveats around that. So that's one thing. Another thing, thinking about that, like usually the people that do the flood frequency analysis and the engineering are pretty separate from the land use planners, the communities, state, provincial, federal regulators that allow or disallow development in the floodplain. There's a really interesting paper that I haven't looked at for a long time, but I know I've had the figure in another presentation, that if you look at the risk downstream of a particular point on a river, building a dam will often reduce the risk of a 100-year flood, but it can actually make populations more vulnerable to the 500-year or the 1,000-year flood, because we think, hey, we put in a dam, we are safe now, we're going to build close to the river downstream because we want to be close to water and greenery, and we want to be there. So maybe for 50, 100 years, they're well protected. And then there is a huge event and people are shocked. They didn't think this could happen because we had a dam, but it's such a huge, rare event that we're actually have made ourselves more vulnerable to total dollars in damages because we've built in that floodplain.
All right, thank you for your answer. That's very insightful. Okay, I have a question in the chat from Yulia. She says that have you seen using graph representations to capture spatio-temporal dependency in these data and then assessing trends over graphs? It may weaken the assumptions behind the more traditional model with stationary conditions.
So I would say I've seen some of that. Certainly that is an area I would be interested in exploring more. And Yulia, if you have more ideas on that, and if an example study comes to mind, I think there would certainly be some opportunities there.
Yeah, the reason why I'm saying is that, you know, my original background actually in time series analysis, and I know how difficult it is really to validate stationarity and how, I mean, how unrealistic this assumption may be, especially when you start, you know, looking at also spatial dependence. So one idea to address it is actually represent the whole process through a graph. Okay, and well, that will be time evolving graph. And you then, first of all, you don't need to rely anymore on Euclidean distances. Okay, and then you can, after that, you can do regression on graphs as well. And you can have, you can also have a trend in the models as well, estimate. So this is something that is, and it's kind of also related to some of the questions that Jeddah asked about, you know, ML part. Then you, on top of it, you can have any, you know, non-parametric models over graphs to estimate forecast and so on. So that's something that kind of, when I was listening to it, it seems to be a very intuitive approach how to model this problems where you may not really have stationarity, and that is kind of artificial assumption.
Yeah, I think there's a lot of opportunity for that. And when people do flood frequency analysis, traditionally they get very focused on individual sites, but with the advent of graph methods, machine learning, there are lots of opportunities. You know, people start looking at lots of sites at once when they go to this regional regression at on-gauge sites. But there are a lot of opportunities, I think, to not be so focused with flood frequency at one site where you have data, but at 100 sites where you have data, and what can you get out of that overall message?
That's right. That's right.
Yeah.
Because you also kind of enrich modeling at each site by looking at the similar sites.
Yes. Yeah.
Okay. Yeah. And that's, so you no longer just do, I mean, if you think about like nodes, it's not like you just pairwise node relationship, but like rather than looking at the neighborhood of each site. And this neighborhood may be defined through Euclidean distance or similarity of previous signal that you observed at each site.
Yes. Yes. Yeah. Yeah. So if there's some papers that stand out to you that we should look at, I would really appreciate if you could send me some.
Yeah, I'll try to. Yeah, I mean, this ideas of using graph representations for spatial temporal data, I mean, I saw a number of papers in ML literature, but it started getting up in statistics as well. But it's interesting that more formal approaches that in statistics existed in like late 90s, when even if you have just a single time series, you, instead of using, for example, autoregressive structure or something, you can have something like a causal graph. So where, for example, Monday, say, Friday may be more dependent on Monday rather than Friday depends on Thursday, where that is typical condition that we have in if we have mixing, yes, so this type of more sophisticated dependencies could be captured by graph.
Yes.
So,
Yeah.
Anyway, so I'll think about some reasonable papers to send. But I have not seen it in application to hydrology, but yeah, I mean, but I've seen in some other applications in, for example, in atmospheric sciences and so on. But anyway, so it seems to be quite intuitive.
Yes, and flood frequency traditionally, and partly because of how the guidance is written, it's so focused on individual sites. But that also makes me think, you know, streams, it's all it's networked. So we've got a site on a large river, but we've got these tributaries with stream gauges, and we're calculating flood frequencies at these sites. But because of climate or land use, one or more of these tributaries may have changing flood regimes, and to network and graph and put all that together would be really fascinating.
That's right. Yeah, and it will be directed graph as well, depending on the flood.
Yeah. Thank
So
you.
I'll try to dig up something with the papers. Yeah. Thanks very much. It's very inspiring talk. Thank you.
Yeah, thank you for the
Thank
talk.
you.
Any other questions from the audience? Okay, there are some comments in the chat.
Okay, so I see the question on the confidence intervals, and so for how they are constructed, I would direct you to Bulletin 17C, and there are details in there. And are users happy with such big intervals? So, you know, users want to see smaller intervals because they, when it comes down to it, they have a target point estimate for the bridge, essentially. So they're not always happy with the broad intervals. So part of our work is also communicating to our partners that we do this kind of work for about the great deal of variability in hydrology. And most people we work with are pretty, maybe it's something they haven't thought about so much as we have, but they're pretty amenable to that message. And then they have to, within their own agency, figure out, are they going to use that mean estimate or go with a higher confidence interval? That also makes me think of the work I did with the U.S. Nuclear Regulatory Commission, where we went to essentially the million-year flood and calculating these. And it varied with sites, but I know there was one site where the confidence bound was like 1 billion cubic feet per second, which in my mind, that is just not usable. And I said something to that in discussions with the Nuclear Regulatory Commission, and they had a very different take than I did, in that they deal with extraordinarily rare events with huge uncertainty all the time, and that they can incorporate that information into their risk models. So part of that question depends on the audience, and it depends on the infrastructure that they're building. If it's for a culvert, you know, they'll use this information, but also go by what size of culverts they've been generally putting in. If there's supply chain issues, what size of culverts they can get, and know that they may have to replace them, and it's not such a big deal. But as you get into bigger and bigger infrastructure, it is a bigger deal. Would the rising and falling land information be useful for frequency analysis? So questions do sometimes arise with changing conditions. Maybe you're moving more from a snowmelt regime to a rainfall-driven flood regime. Is the river rising faster? And that means you have less lead time for warning. That is not incorporated anywhere that I know of into flood frequency analysis. That does make me think of another area, though, that we're looking at. In many sites, there used to be a typical flood season, maybe in the northern United States, north central United States, driven by snowpack. Most floods would happen in March or April. And then some years you wouldn't have much snow and you'd have a summer convective thunderstorm that created a flood. But those were generally rarer, smaller events that you weren't as concerned about anyway. But there's some sites where, and someone part of the project we're working on now, she has a paper that hopefully will come out in the next few months on changes in seasonality, where we're seeing dramatic changes, where a site used to always flood in April and now it might flood anytime out 6 months of the year. Or now it's more of a bimodal distribution where we have some snowmelt peaks, we have some large summer peaks because of increases in extreme precipitation. And that's an area where we can use a method called peaks over threshold. And we're looking at that to see if we can improve flood frequency analysis there. Oh, and thank you for including the statistical hydrology meeting in Boston. That will be a good meeting. Okay, and Janice already had to run, but I agree, this is important stuff. And this is where there's kind of been a disconnect in some of the research community and practitioners. You know, people can come up with super sophisticated, complex methods for flood frequency analysis, but if it's beyond the capability of the general expertise in state and federal transportation, water agencies, it's not going to get adopted. So maybe people got PhDs, it looks good in their research, but how can we help the practitioners on the ground that are building infrastructure? So this is really important stuff.
All right. Thank you, Karen. I have one more question to ask. So how do you include tensor variate data at all where there is multi-way dependencies? And how can, I mean, if you do that, then you also, so what would like precision matrix or covariance matrices of multi-way dependencies inform you with regards to flood frequencies at all?
So this, I've been thinking about a specific application for that, because the streamgage network, the USGS operates across the country, and some states have their own streamgage networks, but we operate a national streamgage network. But the funding of it is very patchwork. We have some of the funding, state agencies, local agencies, tribal entities pay in, and sometimes the streamgage is discontinued because the funding has gone away. And then maybe it comes back and you have a 20-year gap. Or maybe we had a lot of gauges that got discontinued in 1980, but they had 50 years of data and we want to use that data. So people estimating those missing years is and Bulletin 17C mentions that, but record extension, estimating some missing years so then we could do flood frequency analysis on a longer record. And I just need time to do it, but to use like multivariate imputation of missing values, you could use principal component analysis and bring in multiple stream gauges, precipitation data, land use data, and do their methods to do multivariate imputation of missing values using principal components analysis. And I think that would be a much better way to use additional data-informed method to estimate those missing years of record. So that's just one small aspect of what you're thinking of, but there are opportunities there.